I'm JiaBin Huang from University of Arizona, and my research focuses on characterization of substellar companions using adaptive optics. So here we image this companion, 1RXS1609b, using the Magellan AO system, which is on the 6.5 meter Clay telescope in Chile. So the image shows the actual detection at Z prime. And the right panel shows the spectral energy distribution compared with different atmospheric models. So the main finding is we found we have to apply a high dust extinction, about 5 magnitude, in order for the models to fit the photometry. So the black dots are the observed brightness, and red curves shows the models reddened by dust extinction about 5 magnitude. And blue curves are the spectra without dust extinction. So we derive a mass about 12 to 15 Jupiter masses. So the interpretation is the companion might be a low mass brown dwarf and surrounded by a dusty disk. And more information can be found in the paper. Thank you.
Hi, I'm Alex Greenbaum. I'm a PhD candidate at Johns Hopkins University. And you may have heard a little bit about the Gemini Planet Imager coming out with some new results. And beyond the chronograph that's on the Gemini Planet Imager, there's also a 10-hole non-redundant mask that observes in all the same modes. It's an interferometric mode, so it accesses much smaller inner working angles that are blocked by the coronagraph, scales of a few to 10 AU. So it's a complementary mode to the chronograph. And in May this year, we had an extra night of commissioning just for the mask to prepare it for proposals for the next semester. So the mask operates, GPI is an IFU, so the mask operates in both spectral and polarimetry mode. In spectral mode, we can get a spectrum at every image pixel, which is particularly useful, for example, if we have a faint companion that has maybe emission features. So that's one opportunity. In polarimetry mode, we get an image at 2 orthogonal polarizations, and we can use a technique of differential visibilities, interferometric visibilities, to resolve disks around stars close in behind the chronographic spot. The mask is also a pretty useful tool for diagnosing issues with the instrument, like vibrations and low-order wavefront error, which I could talk about for a long time, but I'll leave that off. So if you're interested in any of this, if you're interested in using this mode, I'm at poster 29. There's more details. Thanks.
Hi, everyone. My name is Kimberly Wang, and I'm a PhD candidate at Arizona State University, working with Jenny patients. And our poster has 2 distinct searches for companions to nearby stars. So the first of these surveys is the M dwarfs and multiple surveys, which was recently completed earlier this year. And this is a search for companion stellar and substellar companions to M dwarfs. So we looked at 245 nearby M dwarfs within 15 parsecs with Hipparcos parallaxes, ranging from about K7 spectral types to mid-Ms, mid to late Ms, and we have a combination of both adaptive optics imaging to look for companions from 3 AU to about 100 AU, as well as wide field imaging that allows us to look for companions from 100 AU out to about 10,000 AU, covering the whole separation range of binaries. We have multiple epochs, which allow us to find common proper motion companions to these stars and confirm their physical association, and we're sensitive over this whole separation range all the way down to the substellar limit. So the first paper in the series is on the stellar companions that we found. And from these statistics, we can form some understanding about how often we find companions in over certain separation ranges, what their mass ratio distributions are like, and what their separations are like. And what we're doing right now is we're working on some of the substellar candidates that we've discovered to follow up and see if any of the candidate brown dwarfs that we found in both the AO images, examples seen at the top, and some of the wide, this is a 7,000 AU system, are actually real co-moving companions or not. And if we go to the second slide, the other search component of this poster has to do with looking for young systems from the Gemini Planet Imager survey. So we're conducting a complementary survey to look for young wide-orbit giant planets and brown dwarfs to GPIs target stars using Magellan AO at L prime. And you can see in the plot of mass versus angular separation that we're searching a complementary space outside of 2AU to look for the really wide orbit planets and basically try to form a better understanding of planetary system architectures over a wide range of orbital separation. And I'm at poster 28 if you want to learn more. Thanks.
I guess I'm the special one with a movie. So hi, my name is Rachel Smellin, and I'm a graduate student at the University of Arizona working with Caitlin Cratter on the architecture of circumbinary systems. With the observed Kepler circumbinary sample, there seem to be two kind of strange things. First of all, these planets seem to be fairly low mass. There's a lack of giant planets. Second, they all seem to exist fairly close to their binary star's dynamical stability limit. So the question becomes, nature or nurture? Are these planets formed in situ, or do dynamical processes such as planet-planet and planet-star interactions sculpt these systems over time? To study the dynamic evolution, I use n-body simulations such as the one shown in this movie, where I assume a binary star at the center, shown by the orange and yellow dots flashing in the middle, and then I scattered 10 planets in the system that have been drawn from any one of 4 planet distributions that we've developed. I make no assumptions about stability, so these planets are very dynamically active. We find 2 interesting effects. First of all, the relative loss rates between the single star case and the binary star case are virtually identical, meaning that any given system will retain approximately 2 to 4 planets. However, we find that the loss methods between the binary case and the single star case vary wildly. So, if you would like to know more, I invite you to visit me at poster 26, and we can talk about why these differences arise, and I can tell you why I think circumbinary planets are some of the most interesting things you'll hear about at this conference. Thank you.
Good afternoon. My name is Rosario Franco. I'm from the University of Texas at Austin. Sorry, Arlington. I meant to say it. I was thinking, don't say Austin. I'm working on trying to find orbital stability criteria for an exomoon to survive within stellar binary systems. So what I work with is a system that has 2 binary stars, A and B, a Jupiter-like exoplanet, and an Earth-like exomoon. I perform orbital integration using a software called Mercury, and through that I obtain the orbits in where the Jupiter-like exoplanet survives. That means it does not collide with any other object and it does not escape the system. Once I obtain that orbit, I add the exomoon and I perform a similar analysis. And that's how I obtain orbital stability criteria for this type of system. I am also involved in the analysis of GMRT data we recently got from India in hopes to make the first exomoon detection through radio waves, which is a method suggested by Joaquin Noyola, who is my colleague. And if you're interested to know more about exomoons, just stop me and we can talk. Thank you.
Hi, I'm Rajak Oeda from the Australian National University. You guys already know what exoplanets are, what circumbinary exoplanets are. They're really cool. I only started my PhD 5 months ago, so I don't really have results, but I'll tell you what I plan to do. In the course of my PhD, the question I really want to answer is what is the lifetime of circumbinary protoplanetary disks? Like Jenny Patience mentioned, lifetimes are important to know. So I plan to do this through observational methods and theoretical methods. So with my observations, I want to understand the fraction of circumbinary disks in regions of different ages, similar to the methods of how we found the lifetime of circumstellar disks. Next slide. And then in my theoretical work, the first project I have is to simulate using MHD, hydrodynamic simulations, to simulate the formation of a single star and a binary star. So the left one is the formation of a single star, and the right one is the formation of a binary star. to see how the disk forms and how the angular momentum is transported in the systems, because understanding angular momentum between the two is also important to know about the stability of the disk. And those are two zoomed in images of that. And I also plan to do a parameter study on the stability of circumbinary disks around a variety of binary systems. Thank you.
Okay. Hi, I'm Rixin Li. I just finished my first year in University of Arizona, working with Andrew Yuding and Jack Simon. My work studied the simulations of planetesimal formation due to streaming instability. You might still remember Andrew's talk. The origin of the planetesimals in gaseous disk is a long-standing problem with many barriers to the growth from centimeter-sized solids up to kilometer and beyond. And the streaming instability is a robust particle clumping mechanism to overcome these impediments. And previously, people accomplished this by simulating the gas and the particle with their mutual interaction in a local 3D box, incorporating the vertical gravity from a star. Here, my work, we study how the vertical boundary condition and affect the planetesimal formation in different numerical box sizes. And more importantly, in addition to previously used periodic and reflecting boundary condition, we also explored a more realistic one, the outflow boundary condition. Here is a snapshot of our simulation. The green clumps are where the particles are concentrating. So now please focus on this result, outflow result. So in each row, each line represents one simulation, one box sizes. The first row represents the evolution of the maximum particle density in 50 orbits. They eventually reached 1,000 times the mid-plane gas density, a perfect density to trigger gravitational instability and form planetesimals. The second row here displays the evolution of the particle scale height. They will went down to 0.5% of the gas scale height. That's why my 3D snapshot looks like a 2D plane. And the comparison to the other two cases shows the outflow will lead to better convergency, and the thinner particle layer also stronger clumpings. Therefore, outflow will lead to more efficient and numerous planetesimal formation. So for more details, please see my post at P34. Thanks.
Okay, thank you. Hi, my name is Alex Wyse. I just finished my second year of graduate studies at the University of Delaware, and I'm going to be talking about how photoevaporation and how photoevaporation affects planet migration. So thanks to Richard Nelson for kind of already covering a lot of this stuff. Made my job easier. So the takeaway message from the top diagram here is just that in planet migration, the outer limb-led resonances push the planet inward, and the inner limb-led resonances push the planet outward. And if you remember from his talk, the giant planets actually open a gap, so only the outermost resonances affect planet migration in that case for giant planets. So then, if we combine that with this bottom picture here, which is one of a diagram showing photoevaporation. The idea is the inner disk atmosphere here is bound, so even the highest energy photons are unable to eject the material from make it escape the star's gravity. But once you get out to a certain place called the gravitational radius, or simulations have shown maybe a little bit further inside the gravitational radius, material is able to escape, and what you see is a gap forming eventually due to photoevaporation in these simulations in the late lifetimes of the disk. So when one of these resonances, either the inner or the outer, is in a gap, it's not going to be torquing the planet nearly as much, and the other resonance can overpower it and choose the migration direction. Let me change the slide. Okay, this was originally a video. I don't know if you have a pointer. No, I don't think I uploaded it as a video. It's not a video, is it? There's usually a little arrow down here. No, okay, it's fine. I should have checked anyway. Anyway, so the first panel of the video has a lot of information. So I just plotted the outer 5 strongest resonances for a circular orbit here, and just showing how those kind of coincide with the edge of the planet-induced gap in a disk. So as the disk spreads out, material is going to be filling in this gap and interacting with these outer resonances. But what can happen is if a photoevaporation gap opens around here, then those are no longer propelling the planet forward in type 2 migration, and it can stall it and produce maybe some interesting features in the detected planet distribution. But as far as I can tell so far in my research, this probably won't affect planets in the first few AU that we've seen mostly so far. So maybe further out, like 3 to 10 AU. Oh yeah, see my poster number 36 for more information. Thanks.
Hello, my name is Julia Kaldur. I'm a first-year student at UC Santa Barbara, and I'm working on monitoring the variability of stars that host super-Earth and Neptune-sized exoplanets. The PI of the project is Diana Dragomir, and we started monitoring the stars in November until May, and we observed them every 1 or 2 days using LCO GT, so from Earth, in the VR and I filters. But this project is part of a large program that you have heard about actually this morning during the first pop talk, to observe the atmosphere of the planets. Using transmission spectroscopy and Hubble data. So on the next slide, these are the preliminary data that I have. Here you can see these are relative to GJ3470, and we are using 4 reference stars. 4 reference stars here to look at the variability of the host star, and we can already see from this plot, as I said, preliminary, that the variability is small. It's around 10 or 20 millimax. And from this zoomed plot, we can see that there is a period of 24 days. That is what we expect from previous data. So it's actually good that we are confirming that. And the next steps are to create a weighted ensemble of reference stars to use for differential photometry and filter out the bad nights. So hopefully these points that have larger bars will go away, because there's probably they were taken during poor weather, or they have out-of-date flat fields. Then we will use the multi-filter photometry to constrain the spot temperatures. So this is in the I filter, but we also have data in the R and V. And finally, we will use these constraints and the amplitude of the variability to interpret the Hubble data and take into account the stellar activity. Thanks.
So while this presentation is setting up, let me introduce myself. My name is Maxwell Street, and I am a visiting student at UCSC currently, but officially I'm from NAOC and KIA from Beijing. And today I will be, let's go to the second slide directly. Yes, I will be reporting about some primitive result about planetary system in star cluster. Why this is interesting, because we know that stars are formed in clusters instead of in the field. This is, at least most stars is in the case, due to the consequence of the collapse of the dry molecular cloud. So it could be possible that our solar system and other planetary systems are also formed there. But there's a problem. In such environment, the density is much higher than the solar neighborhood. So my research interest is to investigate the the dynamical stability of planetary system under such frequent perturbation. And to do this, you can observe result with analytical approach, but this is difficult because at least there are 3 bodies, but usually there are multiple planetary systems, so there are more than 3 bodies, and this could bring to very difficult chaos system. So it will be much more feasible to resolve the research with numerical simulation. So to do so, I integrate the star cluster with the code M36++, and then integrate the planetary system with Mercury 6, and then use a so-called Amuse framework to communicate the perturbation from the star cluster to the planetary system. And can we go to the second? Yeah, play this movie, please. So if you plot, so I have like 50 identical planetary systems, but they are located in different locations of the star cluster. Some are at the center, some are in the outskirts. And if this is the outermost planet, and it has the semi-major axis of 100 AU, and so you can see that the eccentricity gets excited pretty soon, and then this gets slower, this gets again slower, but once the eccentricity gets high enough, there will be orbit crossing, and these outer ones will actually perturb the inner ones. I mean, in that reason, the planet-planet interaction will be more important. And also, I have some relevant research about the inclination. They also follow this rule. So if you want to know more about the detail and know more about how I actually implement the technical aspect using by bridging the time step difference, you can come to my poster number 23. Thanks.